I think we're live. All right. Let's start. Okay. It was working right. Let me see. Yeah, it's working. Okay. This was fine. Okay. What we have to do is it's 11 a.m. right? It's just Let's continue, yeah. Let me just bring my notebook first.
Okay. Should we continue?
Yeah. We have finished the conversion part of the radian and degree,
which is supposed to be next.
and now we'll move on.
What's the chain rule of derivatives used for? It's when you have a function inside of a function and you need to do the derivative of that. And you need to differentiate that function.
True.
The derivative for it's when you have a what's the chain rule of derivatives used for? It's when you have a function inside of a function and you need to do the derivative of that. And you need to differentiate that function.
Function inside a function. Really? Can I put it? Lambdas. Sorry. Yeah. Excuse me. Public intercom. And my so C# can actually declare function inside a function in it. Alright. Okay. Thank you, Google. I'm quite sleepy,
Okay,
but
well,
I'll
I'd like
try
to know
not
more
to
in depth
sleep
about
today,
this with
tonight.
radians and how much your practical stuff, because so far this isn't clicking with me, but I want to understand it better. Yeah, so like the use cases for this is exactly the same use case as for degrees. So far we haven't really introduced like a new tool. It's just a different unit, right? But we're gonna get into trigonometry now. Okay, so how are we doing on breaks? It is a pretty good break time. Okay, let's do break until 14. A little bit shorter than 10 minutes, but maybe that's okay. Okay, so I guess I can. Oops, sorry. I guess I can keep answering random questions during the break if you have any. Yeah. Now the cats are not fighting. Now they're. Well, I see Thor is napping in the bedroom. I don't see the other two goobers. How does one calculate the point of refraction given a source target and the refraction index? I don't remember. Isn't that the Fresnel equations? I believe that is. I can see the other two goobers.
Give me a second.
How does one calculate the point of refraction given a source target and the refraction index?
So
I don't remember. Isn't that the Fresnel equations?
Fresnel equations. I have to remember some.
The Fresnel equations. Snell's law. That's the one.
Snell's law. Yeah, the refraction path. Like it is the interference. Actually, when you actually change from one medium to another medium, there is slightly diffraction towards the normal. The light actually bends towards the normal when you actually go from lower refractive index to higher refractive index. There is a slight bend that's called Snell's law. So that's the theta 1 and theta 2.
Yeah, so N1, N2 is the refractive indices of the material.
Yeah, I told you, like there's a different refractive index. Even in optical fibers, there's some core and clady. They use it. So the core part of the refractive index of the core part is much higher than the clady. So the optical rays do not pass through an optical fiber from core to clady. So that's what happened. Even in the optical fibers we use for the internet's data transfer.
Yeah, and then you have your angles here, and then you can just do some shuffling.
This is like sine 1 and sine 2. You can see see over here Snell's law. I'll show you. Snell's law. This is, you can see like this refractive index is lesser than this refractive index, right? N1 is less than N2. So there is a slight bend. This is the normal, and there is actually a slight bend towards the normal. So the Q1 is larger than Q2. So this is called Snell's law. History. Oh my god. Production of page in Ibn Sahih Oh, so this question has been developed by a Muslim guy, I guess. Snell's law. Okay. This is the same thing happened in the optical fiber refraction. See, it's the same thing happens over here as well in the optical fiber. So this is the core part of the optical fiber and this is the cladding, but the core part refractive index is much higher than the cladding, so it won't pass through, it just reflect. The optical rays just reflect and stay inside the core part. See, uh, refractive index of cladding is lesser than the refractive index of core. So yeah, so you have to know all of these things to actually think that for things like air and glass, so the refractive index of air is actually less than the refractive index of glass, so that's why there is a slight diffraction towards the normal when you actually pass a light or laser uh, through the glass actually.
Around to figure out the angles.
This is this is
And Freya, to your
actually
chat
easy
messages,
to
I am
understand
only
if you
reading
relate
YouTube chat
everything
during
with
breaks,
the
and now it's a
game
break, so
mechanics.
I'm reading the chat from my students for the most part.
That's why like you have to know about shaders programming in game
I would
programming
calculate
so
O if
you
I'm
can
playing you.
actually
Oh,
understand
the
how a
intersection
light
points,
works
or
and everything
like
inside a
where it's
game.
hitting the surface. That would be just a plain
That's what
ray plane
I'm doing
intersection
right
test.
here. She is really good
Which you can
teaching
kind
these
of like
things.
write that formula if you want to and then solve
Yeah.
it by hand,
Mm-hmm.
which is a little bit messy. I had that in my math library. In Unity, you can also do it using... Unity has a construct called a plane, which is really useful. So you can do new plane, and then you give this a normal and a point. So in this case, I guess it would be vector3.up, and then some point in the plane, which I guess we can just set to 0. And so Unity's plane function has a plane.raycast. And that is basically what you want to do, right? You want to send a ray into this plane and then get which point it entered at, right? So generally you would have some sort of your initial light ray.
Ray light.
And then you raycast using your ray, and then you get the distance along the ray out of it. So then the intersection points. Oh, this is a curse.
Damn. She's really good at
is light
understanding
ray
math and programming it. It's really difficult.
So this would give you the
Snell's law. Damn. I should actually note it. This thing is fucking crazy. Crazy. Crazy as hell. Ouch. Okay. Outflow distance. Vector 3 intersection point equal to like 3 dot get points comma damn. Oh, head. Ouch. And now we can use the light intersection to get this done. Wait, I have to note some things. Snell's law. Diffraction. Interface. Normal. This is light gain and it bend towards the Q1, Q2, N1, V1, N2, V2. V1, V2 is velocity of light traveling through a medium. V1, V2. Sine theta 1 divided by sine theta 2 equal to n 2 comma 1. which is equal to n2 by n1, which is equal to v2 by v1. All right. Code. Let me write the code as well. Plane equal to new plane. Vector 3. Vector 3 comma up is normal actually. 0. Vector 3 dot 0. Plane dot raycast. I mean, I'm not good at as her because she obviously have more experience than me, but at least I'm trying my best to learn more and more things. I don't know if I can reach that kind of level in my life, but I'm sure I will just try and try until I can. Because I really want to be a good game developer. Right. I'm done with this. Okay.
Well, if you have P, I guess. You don't need Q, then it's overdetermined. But you can do it from either P or Q. Oh, they used imaginary numbers for that? Okay, weird. Oh, that seems really cursed. Why would you do that using complex numbers? What is this about again? We're talking about refraction. When light rays hit a transparent surface, the light ray will change angle. And so someone asked about the angles. We're still on break for another 2 minutes, so. How would you make relative time in a game? Can you reduce game speed for certain stuff? The problem with that is going to be rendering and collision, because then you don't have a ground truth for one state of the world. Then every state is going to be relative to every position and velocity, which gets cursed.
True.
I don't even know how you would set that up, but I imagine it should be possible, and it also depends on how accurate it should be and so forth. Okay. Okay, yeah, I feel like my solution is a little bit more clean than the imaginary numbers, but... Okay. Alright. Then I think we're ready to talk about sine and cosine.
Yeah. Sine is equal to b by hypotenuse, perpendicular by hypotenuse, and cosine is equal to base by hypotenuse.
Oh yeah,
I
by the
know
way,
I don't lose much.
the plane struct is super useful. It also has like, you can project things to the plane. You can check which side something is on. So there's like get side of a certain point. There's plane dot, I thought there was a project. Closest point on plane, that's the same thing as projecting. So you can get the closest point on plane from some other points. Has a lot of useful built-in functions.
Nice. This
It's
plane
also a
function is
struct,
really
which
cool.
is very nice. So it doesn't allocate. So you can just like do very quick and easy operations with it. So that's neat.
So
It's a
all
useful
these
type
planes,
to have in your
raycast,
toolbox.
physics are actually includes in Unity physics and math
Right.
functions.
I think we're ready to resume. Why are shader developers against intelligible naming? The thing is that like the short names that you have in math and shaders, it's mostly because you tend to have, the focus is more on all of the operations together and being terse rather than the specifics, like the specific name of what something is. Because math has a lot of operations and usually not that many variables, whereas in code you have the other way around. And so math and by extension shaders do usually use quite short names in general, because otherwise your equations are going to be huge. So like this line is very long, right? But this is just a minus b, right? So if you type a minus b, this is way more readable, although you have to remember which is which.
Yeah.
And so, but yeah, it's also a little bit of an artifact because variables in math tend to not have more than one letter in their name. Usually the way you solve it in math, I'm just gonna slap it into this document because who cares? So if you have a math equation, the thing is that like if you have a lot of variables, you tend to name them with indices instead. So you would use like C0 or C1 with like subscript. So this is how you would generally do if you have like a lot of things. You just add a subscript, and then that way you have more variables. But in math, you basically never have variables with more than one letter. Yeah, and so basically just continue on like this. Just use letters, use subscripts whenever you need to, and so forth. Which, for better or for worse, math can become pretty unreadable because of this. But again, it's easier to see the structure when you don't have very long variable names.
True.
Yep, so it's kind of a trade-off. They both have their advantages and disadvantages. Anyway, trigonometry. I need to ping students again. Students. We're going live with trig now. Wow, React. Okay, React to we're doing the trigonometry, cosine, sine, cosine. Why use tab size 4 rather than 2? So much waste of space. Your comment is a waste of space. Why use tab size 4 rather than 2? So much waste of space. Your comment is a waste of space. All right, let's do some waves. YouTube chat moments, yes. I'm so judgmental against YouTube chat. There are some YouTube chatters that are good. I don't wanna say that all of you are bad. Not all YouTube chatters, as they say. Okay. Okay. All right. Now we're getting spicy. Time to do another circle. Rate my circle. Oh god, circles are hard. I wish circles were easier. Okay, that one's pretty good. It's a little bit of a potato, but that's okay. Can I like slightly adjust it maybe? I don't know. See how useful the unit circle is? We've been using this so much. Incredible, actually. Incredibly useful tool. Okay. We got our unit circle. So, the cosine and the sine function.
Yes.
Let's say you have a vector. We're just gonna draw a vector on the unit circle, and we're gonna call that V. How do you draw a V? I'm not sure. Like that, I think. Cool.
I was
Then-
just thinking.
Let's say you have an angle on this one. So you know the angle here. And again, we're gonna call it either alpha or theta. I don't know, alpha is cute. And now the question is, what is the x-coordinate of this vector? And then, what is the y-coordinate of this vector? Because
If you want to find the x-coordinate of this vector, it will be p by hypotenuse, p square by hypotenuse square equal to the x-coordinate will be like hypotenuse minus hypotenuse square alpha, right? Let's
if you
see,
only know the
first.
angle, then
I
you need to
forgot,
somehow figure
but
out
I know
these
how to do
coordinates
it.
if you want to convert it to a vector. Because an angle is just a number, and then the vector is like a... It's two numbers, right? You have an x-coordinate and a y-coordinate.
Then if you know that this angle and
Like
this
this, right?
angle will be the similar because of the angle property we
and so
learned in
what
the
the sine and the
middle
cosine
school.
function does is that it just gives you these two coordinates. And that's basically it. And so
Opposite intersection or something.
is the
angle.
cosine
Yeah.
of the angle. And the y-coordinate
Will
the
be
sine
the
of
sine coordinate. Yeah. Yeah, I got it.
I don't know how to write anymore. I just don't.
Sine. Yeah, no, yes.
And so that's what the cosine and the
Yes.
sine is. Given an angle, the cosine gives you the x component of this vector, and the sine gives you the y component of that vector. And so what happens if you increase this angle So you can just keep increasing this. What's going to happen is that as you traverse this circle,
As you traverse the circle, the sign will be getting less and less until it reaches. No. The cost will get less and the sign will increase.
the cosine is going to decrease, right?
Yeah. And the
It's going to
sign will
decrease as the
increase.
vector starts going all the way over here. But then as you come around to this side, the cosine is going to increase again because now the x-coordinate is moving to the right. And so this is effectively how the cosine and the sine functions are defined. And so when you look at the cosine function and the sine functions in a graph, generally it would look something like this, right? So this would be the cosine function, and then the sine function looks exactly the same. It just has a bit of a phase offset.
Yes.
And they have this repeating nature because no matter what you set this angle to, the vector is obviously going to return to the same position when you've gone a full turn around, right?
True.
And so
let me just draw it first, then we'll can listen cosine and sine. This is a vector alpha, and this is the x component, which is called this is the y component. Cos alpha.
So that's why they have this repeating nature.
True.
If you
the sign actually varies from -1 to 1 or something like that.
Here's a super handy website. There we go. There's a super useful website called Desmos, which has a calculator or just a graph tool. This one is super nice whenever you want to visualize like simple functions. So if you have
Desmos.
haven't used this website before, very, very useful tool. Oh, I should probably do the default zoom and there we go, large things. And so if you do the cosine of x,
Sine x. This is the sine x. Okay. So see how it reaches. It reaches from -1 to 1. Oh, if I write. See how it's work. But what's the cost? See, it reaches from 0 to 0. See how it reaches like this. The 0 of the cosine function never intersect, but in sine index. Look, the difference between sine and cosine.
You can now see that the function repeats itself. X is the input value, and the y coordinate is the output value. And so this is the cosine. And if you notice, if you look at the input values here, it goes from 0, 1, 2, 3, 4. And notice where it stops here. Or no, sorry, I meant here. The peak here. The whole period repeats after exactly tau. Well, it says 2 pi because they're cowards. But the you can see that it has radians as the angle because the x coordinate is the angle,
6.28.
and the y coordinate is the output value, which is the x coordinate of this vector, right?
From this.
And so you get this repeating pattern after a full
2
turn,
pi, which is
and the
tau.
turns in this case are measured using radians. And so that's why it's repeating after a value of 6.28, etc. Right? So that's what the cosine is. Of course, we can add the sine function as well. And again, the sine function corresponds to the y coordinate of this vector as we increase the angle. And so this is the relationship between an angle and the components of the vector. Okay. Did that make sense? Should I implement a practical little example so that we have some code experience with this too? Yes. Okay, what about 3D? We're gonna talk about 3D rotations after this. But the thing about rotations is that rotations always happen in a plane. And so rotations are always planar. So it's kind of the only way to talk about them is in 2D. All right, so let's see, what am I? Right, we're gonna implement this. What do we do with this scene? Do I do a new scene?
Yeah, let's do a
Okay,
new
let's
scene.
just do a new scene. It's probably easier that way. Or you know what? I'll just dump it in a parent object. There we go.
New scene will be complicated, but so.
I want to do 2D view. I want to turn on the grid again. We're going to make a new script. We're going to call this trig test.
Okay.
I always have to tab back to Writer and then back to Unity in order for me to open scripts. I don't know why. So it's a little bit weird. Okay. So let's say we have an angle. Like we just want to input an angle. And this one is going to be in degrees. Let's start at 0. Oh, it's a float, actually. And then we want to give it a slider so it looks a little bit prettier in the inspector. So it's going to be 0 to 360.
Okay.
Then we're going to pull out our onDraw gizmos. Okay, so let's say we want to draw a vector based on this angle, so that we have a slider, so that we can change the angle of a vector.
Angle of
that's
a
it.
vector.
That's what we're gonna do now. So
I think.
Maybe we can start out by drawing the unit circle. So that's a wire disk, where vector 3.0 is the center, and vector 3.forward is the normal, and the radius is 1. Okay, just to get our unit circle going. Cool. And now we want to do something with this angular value. This one should draw a vector at that angle that we have as an input here. Then we need a vector for that, and we're gonna call this v. Then we do new vector 2, and then the cosine and the sine function is in the math library of Unity. So cosine is the x coordinate, so we'll pass the angle in there, and then sine is the y coordinate, so we'll pass the angle in there. Now we have the vector, and now we can do gizmos dot, can do array, draw array from defaults to v. And that should be it to create our little rotating vector. Let's see if it works. So now we can set the angle, and now we did the classic example, the classic mistake that you always do. Something went wrong. Can you guess what happened?
Wait, let me guess. Let me see it worked. What do you have done? Is it something about local or world space? Maybe.
Rotating vector. Let's see if it works. So now we can set the angle, and now we did the classic example, the classic mistake that you always do. Something went wrong. Can you guess what happened? Class. Now I'm gonna awkwardly ask class, and then they're gonna have to like raise their hands and awkwardly. Radiance. True. That is true. So we had our thing in degrees, right?
Oh.
But the cosine of the sine function accepts radians.
Radians, yeah.
So, angle in radians is angle in degrees times
And
math
in degrees.
deg to rad.
Degrees to rad. And we have to change it. Angle degree to angle rad. First of all, let's make this one right. First of all, we have to write stack reason variables hashtag and reason variables. For variables we have entity float angle. Put this 0 f, which is range 0 to 360. Oh, my bad. Oh, my hand. I don't know why it's hurting. Randoms. Okay.
So there we go. We have our radians instead. And then we go back, recompile.
Oh,
Have our radians instead. And then we go back, recompile. Bip. And now we have a beautiful little angular thing. We have an angle of 0, can go all the way up to 90,
90,
180,
180.
all the way around. And so there we go. It's a very, very simple implementation of this. And this, again, this could be anything. Maybe you're making a game like Worms, and you're currently setting the aim of one of the weapons of the Worms, like the 2D Worms games. Then you just increase or decrease the angle based on the keys that you're pressing on the keyboard, right? Or the controller. So that's a very, very simple way to go from an angle to a direction, right? Yeah. Feels like a clock. Yeah, making a clock using trigonometric functions. It's actually a really good assignment. Maybe I'll give you that as an assignment. Thanks, it's a good idea. Let's establish a Tau day. That already exists. So I forget which date it is. Is it June 28th? Yeah. All right. So I think by far the most classic use case for me, at least, for the cosine and the sine function is just to convert from an angle to a vector. In fact, I usually use a helper function that does exactly this. So I usually make a function like let's call angle to direction. Then I pass an angle in radians. Then I just turn this into a function. Just return this vector. So now we can just do angle to direction that does exactly this. So I usually make a function like let's call angle to direction. Then I pass an angle in radians. Then I just turn this into a function. Just return this vector. So now we can just do angle to direction. We pass in our angle and radians. And then there we go. So my math library has this built in. If you don't want to write your own. But yeah, so this is effectively a very, very, very common use case of the cosine and the sine function.
Static functions. Functions. I forgot the static functions.
questions about that? Did that make sense? No questions. It's either very good or very bad. One of them. Or a mix of both. Oh yeah, so this is a relatively new C# feature. This is called target typed new. In some contexts, the compiler can know what type this is, but generally you would do new vector2 in that case. It knows what it is in this case because the method is returning a vector2. Yeah. Okay. I don't know if I should react to YouTube chat. My YouTube chat is being incorrect. I don't know how to... I shouldn't respond. I shouldn't read it. Oh, jeez. But yeah, so that's why writer is agreeing out a lot of variables. Okay, so this is just a very simple use case. So like you mentioned, like if you want to make a clock in a game, you would set the angle based on time, right? So you would increase this angle just based on time times some value for how quickly it should move, right? And of course you can just set this to a time value. So maybe we wanted to spin maybe you wanted to spin like one turn per second or something like that, right? So the way we would do that is that we want to set the I used the arc cosine of the dot product in the previous assignment. Yes, we're gonna get to that right after this. So if you maybe want to make this like spin one turn per second, then we could just set the angle in turns directly to your time value. So like I guess editor application dot real times in startup times in startup. There we go. So maybe we have a time value here, and then we want to convert this to radians, right? And so we have to multiply this by tau, which is pi times 2. So now this one should move over time if we set our viewports to animate. There we go. There we go. What a beautiful animation. So now it's doing 1 turn per second. Yeah. So that's doing. Here we go. So now this one. should move over time if we set our viewport to animate. There we go. There we go. What a beautiful animation. So now it's doing 1 turn per second. Yeah. So that's anytime we want to animate something in a circular motion, or you want to set the angle of something. It could be I don't know. We've been doing a lot of turrets. You can set it directly based off of angles like that. Yeah. So there you go. That's the sine and the cosine. All right. I don't think there are any questions about that then. Should I continue? Guessing? Ready to go to the arc cosine, or I guess there are 2 more things we should talk about before we go to the arc cosine. So you have probably heard of a third function called the tangent. So the tangent of an angle. So what would the tangent of the angle be in this diagram? The name kind of gives it away, because the tangent of this angle is...
Tangent will be this one. Tangent will be sine by cos.
Actually, the length of the tangent to the circle at that point down to the x-axis. So this right here, the length of this one is the tangent of the angle. And so one thing that is a little bit weird about the tangent, I should remove this, is that if you move the vector like far up here, right? If you rotate it all the way here, then the tangent is going to go, it's going to become very long, right? So then it's just a very huge value. And as you hit pointing directly upwards, the tangent is actually undefined. The tangent sort of goes to positive infinity here.
Infinity, yeah.
And then when you flip over to the other side, you get the same length here, except it's a negative value. And so the graph for the tangent kind of shoots off to infinity, and then it comes back from negative infinity. And so it looks a little wonky. So the tangent of x looks like this. As you can see, it kind of increases, shoots off to infinity, and then it comes back from negative infinity, and then it comes...
This is cot x cos by sine.
Back there, and then it repeats the pattern. What are the use cases for tan? One of the most common use cases for all three of these is to solve triangles. And the reason for this is that all of these form different right-angled triangles. Because you can see that there's a right-angled triangle here directly, where one of the sides is the cosine, right? And then this one also forms a triangle, a right angle triangle, and the tangent also forms a right angle triangle here, right? This is a 90-degree angle, and this length is the hypotenuse of the triangle. And so one of the use cases for the trigonometric functions is to solve triangles. And so quite often you end up with situations where you have some right angle triangle, and then you know some things of this one. Maybe you don't know everything. Maybe you know this angle, so let's call that alpha, and maybe you know how long this side is. Let's call that, actually, let's call this theta. So if you know the angle theta, and then maybe you know the adjacent side, how long this side is, then you can calculate the other two sides using the trigonometric functions. And there are lots of different ways to do triangle solving. There's just a lot of them, but they all come back to this relationship right here. If you want, you can memorize all the different solutions to this. So if you don't want to do that, then I made a triangle solver because I'm lazy and I don't want to look this up every time. I made a triangle solver, and so if you click these, you can see that you can see how to calculate the rest of the information on.
This one's in this chapter.
Of this triangle. So I have this little interactive triangle solver, but you can see that you have all of the trigonometric functions pop up here, depending on what you activate or deactivate. Here's a link if you want the triangle solver. But the point is that you can use these trigonometric functions to solve for unknown sides of a triangle. Is sine cosine, wait, tangent is sine cosine, right? Then it shouldn't be shorter. Then shouldn't it be shorter as the angle goes upwards instead of longer? Well, so the tangent is the length of this one. So this is the this is what the tangent function outputs. And again, if we increase the angle here, we make an even steeper angle, then the value of the tangent function is going to be the length of this long line. So then the value of tangent increases to infinity as we approach 90 degrees at the top.
90 degrees. Yeah.
If that makes sense.
Mm-hmm.
But sine divided by cosine is smaller in that case? Well, in that case, I'm guessing it's the other way around.
You have to stop it otherwise. Flood things up. Time sensor.
It's cosine divided by sine, right? I forget the... I forget which order it's in.
That is true. What tan? Cosine. Tan
Where's
is
the
basically
definition of
sine
tangent?
divided by cosine.
Can't find it. As opposite divided by adjacent. Yeah, that makes sense. Yeah, then it's sine divided by cosine.
Cosine.
And
yeah,
sine
I know that.
is
Right?
increasing up. It's approaching
Yeah.
1, and then cosine is approaching 0. So what tangent is approaching is 1 divided by 0, right?
0, which is infinity.
So sine divided by cosine is not smaller in that case. But yeah, I should probably also mention that the tangent can be defined using the sine and the cosine. So there we go. All right. And so what happens basically is they get a division by 0, and that's why it shoots off into infinity, and that's why the tangent of 90 degrees and the tangent of 270 degrees is undefined. But again, it's used in triangle solving, so anytime you have a right angle triangle, or even any triangle, and you just know a few of the angles, you can use trigonometry to solve for the other angles. Yeah. I thought the green line was sine. It is. It's just that the green line represents the y coordinate, not the length of the green line. So sine of alpha is the vertical coordinate of this line, but not the length of the line. The length of this line is cosine. So it's a bit of it can be a little bit confusing which one you're interpreting it as. And so it can go either way. Okay. Tangent is parallel to the y-axis. YouTube chat, shush. You can draw it in many different ways. This one is valid. Trust me. Do the math. Cool. Okay. So when you learn about this in school, you are endlessly solving triangles, and then you do nothing more, and that's kind of annoying. And we don't like doing that. It's kind of boring. And so that's why we use triangle solvers to not have to do that over and over again. But it's useful to remember that this is one of the use cases for the trigonometric functions. Okay, so now there's one more thing we need to talk about with regards to these functions. Math in general was tiresome like that. That's true, yeah. Okay, so let's see. Oops. Just cleaning this up a little bit. Or maybe I should just draw a new circle so we don't clutter this too much.
Give me a second. Let me understand something. All right. I'm back. Let's continue.
No, I think we might be good.
So,
All right. So let's say
I think let's
we want to
continue
do
till here.
the opposite of this. So previously, when we were looking at the cosine function, sure, we know that the cosine of our angle alpha, that gives us the x component of v, right? So v dot x or v subscript x. So with the cosine, we get the x component of our vector, and that's great. But what if we have the x component and we want to figure out what is the angle? Like, let's say we already know the x component of the vector.
Give me a second, okay.
But we want to get an angle out of it. So how do we do that? Well, there's a very handy tool called the inverse trigonometric functions, where we can use that to shuffle things around as usual. We do algebra and move things around. So the inverse function lets us kind of cancel out the cosine function. And so what we get is something called the arc cosine. Usually you type it like with just an A. So arc cosine of v dot x. Let me just move that. You sometimes see it written as this. So you have cosine to the power of -1. So sometimes it's written like this. Both of them mean the same thing. This is the arc cosine. It is the inverse cosine function. And so we can kind of use our this coordinate. So if we know the component, we can get the angle out of it. And the one of the use cases for this is actually something we've done before. Because when we talk about the dot product, where is the dot product? Remember that when we had normalized vectors, we can actually use the arc cosine to get the angle out of it. Because then we actually have that exact use case. We have two vectors here, a hat and b hat. If we go back to our trigonometry here, those two vectors is the vector v and the x-axis. And so this, what you're looking at here, is the dot product, right? We're projecting v onto the x-axis, and that is the cosine of alpha. And so if we do the arc cosine of the dot product between the two vectors, we get the shortest angle between those two vectors. And this actually leads us to another definition of the dot product, because this is not the only definition of the dot product. Let's scoot a little bit. So this one is a little bit more wordy, but I believe in you. So we have A dot B equals the length, I should probably do taller ones, the length of A times the length of B. It's a lot of vertical lines going on here. Should probably separate these a little bit. Times the cosine of the angle between them. So I'm just going to write that as theta. And so this is also a definition of the dot product. And so the dot product is
nice.
actually very closely related to the trigonometric function.
Length of A
Um,
into length of B
so there we go.
by
This is a second definition
cos
of the dot product.
theta.
And so the reason we can use it to get the angle is that if A and B are unit vectors, in other words, they're normalized, so we have these hats on top of them. If they are normalized, then
We are
A
getting
and
the
B
shortest
just have a
angle.
length of 1. So this is 1 multiplied by 1, and that's the identity
Cosine of cos theta.
multiplication value, right? And so it just does nothing. And so if these are normalized, then A dot B is just the cosine of the angle between them, which is super useful. And so that's why we can then use this to get the angle. Because if we just have A dot B equals the cosine of the angle, then we do the arc cosine on both sides, and then we get the angle theta out of this. So we can erase that. And we have our angle theta. And so this is a very classic use case of the dot product, just to get the angle between two normalized vectors, which I think is kind of cute that you can do that. Okay, did that make sense?
Yeah.
I hope it did. A lot of people, whenever I talk about the dot product, like the first definition, what am I doing? My computer is acting up. Whoa. I'm still live, I hope. I kind of messed with the stream window. Degrees, angle, or radians? Generally radians. If something is unspecified, it's always radians. And so, radians. Yeah, so quite often when I talk about the dot product, why can I not draw anymore? I can't. It doesn't add anything to the canvas. I have my brush. Opacity is 100%. Okay. I'm just gonna reopen this document. Oh, I might have had a selection somewhere. Yeah, so quite often when I talk about the dot products, a lot of people want me to bring up this equation immediately, but I feel like this equation is really confusing unless you've talked about the cosine first. So that's why I kind of withhold. I withhold information from all of you. Imagine that. Because I feel like this definition only makes sense once you sort of know what the cosine is.
Cosine means.
Yeah, so that's the other definition of the dot product. And these two are exactly the same. You get the same results, like whichever one of these two you're using. Okay. And so if we want to, we could now rewrite our trigger function to use angles instead of using this like just the dot product result. Do you want me to do that on stream, or like I don't know if you want like practical examples like that. Yes, okay.
Okay. We can continue out from here tomorrow. And this is it for today. I think I'll just write these little bit code so I can actually. Okay. This is public plus trigger mono behavior money behavior, and let's start. Hashtag variables range 0 to 360. Now we have to declare our float type public. There's actually a way to do things, like if you don't want the user to understand, I mean, manipulate this value outside your editor, you can just do this. Oh, sorry. Float. This is so this right here, this variable cannot be accessed outside the class, but you want to access it, right? You want to access it inside the editor, so you can like do this serialize field, and now you can access it inside the editor, but you cannot access it outside the class. It's just for the editor stuff. But public float equal to 0f and reason I don't need to write the reason. Static, so I have to understand the static functions. I forgot something you cannot change. Distance. Arid. X comment component is given by the cost, so we'll write the cost. Dot cost and red f dot sign and red, and it's done. Okay, this moves. Just a second. This though it is. Dot is forward. One F. Done. Okay, we are done for today. I think I wrote down things. This is done. All right. Thank you for today, guys. We'll see you tomorrow again. You can continue for tomorrow. The use case of the cos and sine, more often tan as well. So let's